Space, a vast frontier still largely unexplored, beckons us with new challenges and opportunities for discovery. Is there intelligent life somewhere in the universe? Does life of any kind exist in the immense realms beyond Earth? If it does, how do we go about finding it? How would we make contact with intelligent life forms? And how do we know if extraterrestrials have already visited the Earth? Human beings have been asking questions like these for a long time, and the popularity of books, movies, and television programs on the subject of aliens is testimony to our fascination with the idea of extraterrestrial life. Today, serious attempts to find answers to these questions are underway. What are we doing, and what have we learned so far is the subject of this program. As we consider the topic, is anybody out there? Since the end of World War II, reports of unidentified flying objects, or UFOs, have been the subject of much controversy. While most reported sightings can be accounted for, often as weather balloons or aircraft of known origin, some remain that defy easy explanation. In fact, surveys indicate that up to 1/2 of American adults think it's possible that the Earth has been visited by technically advanced extraterrestrials, while others discount UFOs as the products of secret government projects, not aliens. Area 51 is a not-so-secret airbase in southern Nevada that has long been the testing site for America's most advanced aircraft. Over the years, the public has reported UFO sightings in this area, including some that turned out to be the F-117A stealth fighter and the B-2 stealth bomber, years before they were publicly shown. Most mainstream scientists don't think there is evidence to support the claim that intelligent extraterrestrial beings are actually flying around in our skies.
Well, I think that there's probably lots of intelligent life out there because there are lots of worlds out there, and what's happened on this planet doesn't seem to have been so special, at least we don't think so. But I don't think that they're visiting us, even though between 1/3 and half of the American populace seems to think, yes, the aliens are here buzzing the skies and occasionally landing where the evidence has all been collected by the government and taken away somewhere. But I just don't think that the evidence is very good. If you're going to say, hey, they're here, then why not show me sort of a radio knob from the UFO or a really good photo, or if you get abducted and taken aboard a ship, grab a ballpoint pen off the dashboard or something. Never happens.
From time to time, the U.S. Air Force and NASA have been involved in independent investigations of UFOs and the possibility of alien life on other planets. From 1947 until December 1969, the U.S. Air Force actively investigated reports and sightings of unidentified flying objects, or UFOs, under several projects, including the most well-known called Project Blue Book. But after studying all of the available facts, it was determined that nothing would be gained by further investigation, since there was an absence of tangible evidence.
There's no evidence that ET has ever visited the Earth. So even though I'm optimistic that the universe is teeming with life, I'm pessimistic that they've ever visited us. There are a lot of UFO reports, and people say they've seen flying saucers and all kinds of abductions and things like that, but none of them have any credibility or anything that you can follow up on. There are different reasons that we get these UFO reports. The very first flying saucers were not seen until Jules Verne wrote about flying saucers, and then people started seeing flying saucers. So we know that some of it's suggested and some imagined. And then we also know that some of it's hoaxes. Some of the famous abduction movies and things that we found the models when the guy moved out of his house. He forgot to clean out his attic, and we found the flying saucers hanging on the string.
The search for extraterrestrial intelligence, or SETI, is a field of inquiry that seeks evidence of intelligent life elsewhere in the universe, not by going there or waiting for them to come here, but by looking for some signature of their technology. The emphasis is not just on finding life, but finding intelligent life.
Intelligence for us means that they're technologically capable of building a radio transmitter or a powerful laser or something that could signal across the distances between the stars. And so what we try and do is eavesdrop on any such broadcast. If they're sending a radio signal our way, we could pick that up and know, well, there's something out there that's at least smart enough to build a radio transmitter. So that's what SETI's about.
In the early 1970s, NASA's Ames Research Center began considering the technology required for an effective search. By the late 1970s, programs to build equipment were established at Ames, as well as at NASA's Jet Propulsion Laboratory, commonly called JPL. In October 1992, NASA began a detailed search for radio signals from other civilizations under the NASA TOPS program, also known as SETI, the Search for Extraterrestrial Intelligence. But 1 year later, Congress directed NASA to end their SETI project, citing pressures on the U.S. federal budget. Today, no branch of the United States government is involved with investigations into the possibility of advanced alien civilizations on other planets, or for investigating unidentified flying objects. In 1994, the SETI Institute, a private, nonprofit corporation in Mountain View, California, largely replaced the government project.
The SETI Institute was initially formed by a group of people who were interested in conducting the SETI research that NASA was funding in an economical way. And so they set up a private nonprofit organization to be able to maximize the research dollars.
SETI scientists have used radio receivers as well as telescopes looking for flashes of light to search the sky for some sign of extraterrestrial communication.
You need very good electronics. It has to be sensitive. And you also have to have some technique for deciding whether a signal that you pick up is actually ET or whether it's just interference from other human activities like the telecommunications satellites we have, or maybe the cell phone tower down the street. All those produce signals too, so you have to be able to sort all that out. So while in principle it's pretty easy to think of how you might eavesdrop on signals, to actually do it is a pretty complicated thing.
From 1995 to 2004, under the name Project Phoenix, Institute scientists and engineers conducted the world's most sensitive and comprehensive SETI program. During its 9 years of operation, Project Phoenix observed and processed thousands of signals, but found no evidence of another technological civilization in our galactic neighborhood. The signals were all earthly interference. The Allen Telescope Array at the Hat Creek Radio Observatory will serve as the site for the sequel to Project Phoenix.
The Allen Telescope Array is a very innovative instrument, and it's really putting forth the new design for doing radio astronomy by using small, much less expensive radio dishes, many of them, to comprise a big collecting area versus building one giant dish. We think that we'll be able to complete this telescope for someplace between 1/4 and 1/2 the cost that would have been spent had we built one big giant dish of the same collecting area.
The Milky Way galaxy is 100,000 light years across and contains more than 200 billion stars. Which way should we point our antennas and telescopes? What frequencies do we tune to out of the billions of possibilities? A few simple assumptions about the conditions necessary for life will help guide our efforts. The first assumption is that the vast majority of life forms in the galaxy are carbon-based. This is true for all life forms on Earth. Carbon is excellent at hooking up with other elements to make the complex molecules that underpin life. The presence of liquid water is also a useful assumption, as it provides an excellent environment for the complex chemistry that eventually could develop into life. A third assumption is that life is more likely to have formed on a planet warmed by a star like our Sun, or a little smaller. Stars larger than the Sun have relatively short lifetimes, probably not long enough for intelligent life to emerge. Only 10% of the stars in our galaxy are Sun-like, and of those, about 1,000 are within 100 light years of Earth. This would seem to be a good place to begin interstellar listening efforts. But to find a radio transmission from an alien civilization would mean searching the heavens on most of the useful radio frequencies, and there are billions that could be used. To make the problem even more difficult, an alien civilization would most likely broadcast using a narrow beam directional signal. The odds that we on Earth would pick up that signal are quite small.
One of the big problems in SETI is that it's a huge search space. We don't know where to point our telescope, and we don't know what frequency to look at, and we don't know what kind of signal type it's going to be. And so we can't do a thorough search right now.
So do we give up? What are the odds that intelligent life with the technology to send radio signals through space exists somewhere in the galaxy? During the 1960s, radio astronomer Dr. Frank Drake was interested in quantifying the probability that intelligent extraterrestrial life exists in our galaxy. First presented in 1961, the Drake equation, as it has come to be known, was developed to assess the practicality of looking for signals sent by alien societies.
The Drake equation is a formula which gives us an estimate, presently a very crude estimate, of the number of detectable civilizations in our galaxy. That number, of course, is very interesting in its own right. You know, how many other civilizations are there? But it also is very important in guiding the planning of our searches, setting the requirements our equipment must meet, how much we must search, and in the end, how much it's going to cost.
The formula is a product of 7 terms that yields N, the number of galactic civilizations that are potentially broadcasting. Let's look at each of the factors. R is the rate of formation of stars suitable for the development of intelligent life.
The only factor in the equation which we knew for sure 45 years ago was R, and it was known very well. It had been established by astronomers studying the population of different kinds of stars at different ages in our galaxy. That number has not changed. It's about 20 stars per year for our galaxy.
F sub P is the percent of those stars with planetary systems.
45 years ago, we had no direct knowledge of any other planetary system. We didn't even have clues. Today, of course, we know the answer to this because one of the greatest discoveries of the last decade, in fact, the last century, has been the detection of planetary systems beyond our own. As of right now, we know more than 150. Our best estimate now is still F sub P is about 1/2.
N sub E is the number of planets per solar system with an environment suitable for life. N sub E has probably grown in the past decade as astronomers have realized there are half a dozen or so objects in our solar system that might have cooked up life. Earth, of course, possibly Mars, maybe Venus, and some of the moons of Jupiter and Saturn.
In our own system, we have a satellite, not a planet, a satellite, Europa of Jupiter, where the outer envelope is at a temperature of hundreds of degrees below zero, but it is covered with a layer of ice about 6 miles thick, and underneath that ice there is an ocean with more water than all the oceans of Earth, liquid water, in a place where it should be frozen, but it's not because of the insulation of this layer of ice. And so it too could be a suitable abode for life. And this has told us that, in fact, things such as a layer of ice or a strong greenhouse effect can cause planets to be habitable that, according to our naive theories, would not be. Nevertheless, in fairness, we still say that the number of potential planets in each system may typically be perhaps 2.
F sub L is the fraction of suitable planets on which life actually appears.
How did life originate? What we've discovered is that the origin of life is very easy on a planet like the Earth. If you have a body of water and some carbon-based compounds and some sources of energy, this can be starlight, it can be lightning bolts, it can be the heat of deep-sea vents in the oceans. If you have any of those things, you produce the fundamental chemical building blocks of life as we know it.
We know for certain of at least one planet in our solar system that supports life, Earth. So F sub L, the number of planetary bodies in a solar system suitable for the evolution of life, is estimated to be 1. But the appearance of life is only the beginning. F sub I is the fraction of those life-bearing planets on which intelligent life evolves.
This is the one which is still very controversial. There are eminent paleontologists who look at the fossil record of life on Earth and see that there have been literally hundreds of thousands, millions of different species in the history of the Earth, but only one became intelligent. And they suspect because of this that perhaps intelligence does require some particularly improbable steps in evolution, and that intelligent life is rare. On the other hand, there are equally eminent paleontologists who look at the fossil record and see an entirely different picture. They look at it and they see that the one thing in the fossil record that has always increased has been the size of the brain. So, as you might guess, I will lean towards the size of the optimist and lean towards the idea that F sub I is close to 1. Now, you need time, you need 4 billion years or so, but given 4 billion years, you're going to get intelligence.
The next factor is F sub C, the fraction of civilizations that develop technology and who are willing and able to release detectable signs of their existence into space.
Technology allows you to live in climates that otherwise you could not survive in. It allows us to grow more food so we can support a growing population. So there are very powerful motivations for the development of technology, and what that says then is that intelligent species will quickly discover that technology is of great benefit to it and will develop it. And so there again we think F sub C is very close to 1.
Finally, L is the length of time such civilizations release detectable signals into space.
It's the big unknown. And we've always thought it might be a few thousand years. We can't do any better than that today. And unfortunately, we will not know the answer to what L is until we have succeeded in finding some other civilizations and finding out how long have they been transmitting, whatever it is we're detecting. We've been detectable for about a little more than 50 years now. So that, in a way, gives us some idea as to what the longevity L might be. It's at least 50 years if they're like us. The number I use, and you can tell now from this discussion that it's pretty much a guess, is 10,000 years. That allows for just a very small percentage of civilizations to transmit for millions of years. That's all it takes, and L is 10,000.
Okay, we've done the math. So what's the answer? According to Drake, the first 6 factors multiply out to a number close to 1. It's the last, most uncertain factor, L, that determines the value of N.
So if L is 10,000 years, N is 10,000. And your first reaction is, wonderful, there are 10,000 of them out there to discover at this very moment. We just point our telescope in the right direction and tune to the right frequency. There's 10,000 of them we could find. So that's exciting. On the other hand, if there are 10,000, it means that only 1 in every 10 million stars has a transmitting civilization.
So, do we give up?
The capabilities are doubling every year. We used to listen to 100 channels at once. Now we listen to a billion channels at once. And the reason is because it's limited by computing technology, which is the best kind of limit to have because it grows so fast.
One exciting area of research that will have an impact on estimating values for the Drake equation is the recent discovery of extrasolar planets. That is, planets circling stars other than our sun. For many years, extrasolar planets were thought to exist, but astronomers didn't have technology to detect them. Finally, on October 6, 1995, the first extrasolar planet around an ordinary star was discovered. Planet 51 Peg B orbits a sun-like star in the constellation Pegasus. Finding it was a complete surprise to astronomers.
The biggest surprise was that this planet, which was about as big as Jupiter, orbited its star in just 4 days. Now Mercury, which is the closest planet in our solar system, takes about 88 days to go around the sun. So this planet seemed like it was right up against the sun. And it surprised astronomers, and it made them doubt the validity of the interpretation, whether or not the planet was real.
The planet 51 Peg B is also the first confirmed extrasolar planet found using Doppler spectroscopy, a way of using changes in the wavelengths of light to detect movement. In discovering extrasolar planets, scientists make use of the fact that as a planet orbits a star, the planet's gravitational pull causes the star to wobble. This is called the Doppler method. When the star wobbles toward the Earth, its light waves are shifted to the blue end of the spectrum, and when it wobbles away from the Earth, light waves are redshifted. These spectral data shifts help scientists determine the size of the planets and their orbital characteristics. Since that first extrasolar planet was discovered, more than 100 others have been found using the Doppler method, and the list is growing.
Now, none of these planets is like the Earth. They're too big. They're all more like Jupiter than they are like the Earth. But that's a limitation of the kind of techniques that we use to find them. And that's going to change because in the year 2007, 2008, the Kepler mission is going to be launched. That's just a telescope in space. But it's a very specialized telescope that's designed to find planets around other stars that are the size of the Earth or the size of Mars or even a little smaller.
So how will the Kepler mission detect these considerably smaller Earth-like worlds at great distances? First, astronomers can concentrate the search in the most likely areas. Scientists have defined a habitable zone, the distance from a star where liquid water can exist on a planet's surface, a necessary condition for the evolution of life.
The very simple definition of a habitable zone is a distance from a star where it's not too hot, okay? If the planet's too close to the star, it gets hot. You can imagine you push something up closer to the star. And in that case, any liquid water is going to just turn into steam and escape from the planet. Okay, too far away from the star, and it becomes very cold. Look at the surface of Europa. It's an icy surface. So the habitable zone, in the simplest definition, is a place in between where it's just right, the sort of so-called Goldilocks zone, not too hot, not too cold, just right for liquid water to exist in oceans.
Until recently, the Doppler method was the only way scientists had to detect extrasolar planets. And while it works well for finding larger planets, it doesn't work as well for detecting smaller Earth-like worlds. Instead, Kepler will use a technique called the transit method.
The Kepler mission will select a subset of those stars that are in stellar types that are similar to the Sun, plus or minus a bit, and then look very carefully for that time when we're lined up with the star and lined up with the planets around that star, and look as the planet passes in front of the star and blocks out a minuscule amount of light. That's called a transit. With the precision that Kepler will be able to measure the light from all of these stars simultaneously, we should be able to pick out the signature of planets the size of the Earth in Earth-like orbits around stars more or less like the Sun. And in doing that, we hope to find habitable places, places where liquid water could exist.
Once Kepler identifies the most Earth-like planets, other follow-up missions are planned to learn more about these worlds. By gathering the light reflected by a planet and breaking it down into its component colors, scientists should be able to tell if life exists on that planet, and even how far advanced on the evolutionary scale that life is. Finally, if we find a planet with life, we'd want a picture of it.
The long-term vision of NASA is to be able to take pictures, images of the planets. But we're going to have to be patient. No one knows how to do this yet. These are projects for the next generation of astronomers, of engineers, of biologists, anthropologists. All of these disciplines are going to have to come together. Chemists, everyone will have to contribute to solving this problem.
Within the decade, we should find hundreds of Earth-sized planets in habitable zones. We already know that planets are plentiful, but is life? We may know the answer in our lifetimes.
We think there's a lot of diversity of life forms on Earth, with all species of insects and birds and animals and humans, and that must be just a tiny sampling of what else is out there. So it makes it pretty exciting.
Space presents a limitless frontier for exploration. Are you ready for the challenge?